Welcome to the deep dive. Today we're venturing into, well, a really critical world, non-destructive testing, or NDT.
Absolutely essential stuff.
And our focus, two foundational methods, really powerful ones, radiographic testing, RT, and ultrasonic testing, UT.
The big two, in many ways.
So for you listening, our mission here is to kind of peel back the technical layers. We want to get to the core insights of how these technologies, well, how they ensure safety and quality.
Right, in things like welds, critical components.
Exactly. And the key is they do it without damaging the material itself.
That's the whole point of NDT, isn't it? Non-destructive.
We'll look at their, fascinating differences, but also how they actually work together, how they complement each other.
It is remarkable when you think about it. NDT methods, they really underpin the integrity of so much around us. Infrastructure, manufacturing.
Things we rely on every single day.
Definitely. And they tackle that fundamental challenge. Yeah. How do you really know what's happening inside something, deep inside a weld?
Without cutting it open.
Exactly. Without destroying it in the process. Mm-hmm. And that's precisely where RT and UT come in. They're indispensable.
So we'll dig into how they work.
Yeah, how they work, their unique strengths, and importantly, why choosing the right method for a particular job is so vital.
Okay, great. So with that groundwork laid, why NDT matters, let's peel back those layers. How do they actually work? Starting with RT.
Sounds good. Radiographic testing.
At its heart, it seems like it's all about seeing through materials, right?
That's a good way to put it. You pass a beam of penetrating radiation through the object.
Like X-rays or gamma rays.
Exactly. Those are the main types. And after that beam passes through, the radiation that makes it is collected, usually on radiographic film, traditionally anyway.
And that film shows what? Differences?
Differences in absorption, yeah. So think about it. If an area is thinner or maybe less dense, more radiation gets through.
Making it darker on the film?
Right. More exposure, darker image. And conversely, thicker or denser areas absorb more radiation.
So they appear lighter.
Precisely. You get a shadow picture, essentially, of the internal structure.
Like those airport security scanners. That's radiography.
That's a form of it, yes. Real-time radiography looking for density differences.
Yeah.
So a relatable example.
Okay. So you mentioned the radiation sources, X-rays and gamma rays. What's the difference there?
Good question. They're fundamentally different in how they're produced and their properties. X-rays first.
Oh, sure.
Okay. So X-rays are generated electrically. You accelerate high-energy electrons and slam them into a metal target inside an X-ray tube.
Okay.
And what that does is produce a continuous spectrum of radiation, meaning you get a whole range of energies in the beam.
Like a dimmer switch on a light, you can adjust it.
Sort of, yeah. You can control the energy level. Mm-hmm. Conventional X-ray units, they're good for steel up to maybe 60 millimeters thick.
60, okay.
But then you have bigger machines, more specialized ones like betatrons, linear accelerators. Mm-hmm. They can penetrate much deeper. We're talking 300 millimeters of steel, sometimes more. And a key advantage of X-rays, especially the lower energy ones within that beam, is they tend to give you better radiographic contrast. Better sensitivity to small changes.
So a clearer picture, potentially.
Potentially, yes.
Yeah.
More detail. Now, gamma rays, they're different.
How so?
They come from nuclear disintegration,
Sure.
from radioactive isotopes decaying.
Okay, so not electrically generated.
No, it's a natural, or artificially induced nuclear process. And unlike X-rays with their continuous spectrum, gamma rays emit very specific fixed energies, like single notes rather than a whole chord.
Ah, I see. Fixed light bulbs, not a dimmer switch.
Exactly. Historically, people even used naturally occurring radium, but it was hazardous, produced radon gas, and the quality wasn't great.
Right.
But since the nuclear age, we've had artificially produced isotopes.
Right.
Common ones you hear about are like thulium-90 for thin sections, ytterbium-169 for a bit thicker.
Okay.
For welds, probably the most common is iridium-192. It covers a good range, maybe 10 to 75 millimeters of steel. It's like a workhorse isotope.
And for really thick stuff.
Then you look at cobalt-60. That can handle, say, 40 up to 150 milliliters of steel. Big penetration power. But the downside is the shielding needed is really heavy and bulky.
So comparing them, X-rays versus gamma rays, what are the practical pros and cons for someone actually doing the inspection?
Well, gamma sources, their big advantage is portability. No power needed, right? Just the isotope in its shielded container.
Great for field work then.
Absolutely. And the initial equipment cost is usually lower. But, it's a significant but, the radiograph quality is generally inferior to what you can get with X-rays.
Less sharp, less contrast.
Typically, yes. And there's the constant radiation hazard. If your equipment's shielding or your safety procedures aren't top-notch, it's a risk.
And the isotopes don't last forever?
No, they decay. They have a limited useful life, so you have ongoing costs for replacing them. Over the long run, gamma can actually end up being more expensive to operate.
So it's that classic trade-off, portability and lower initial cost versus image quality control and maybe long-term operating cost.
That sums it up pretty well. Mobility versus precision, and always considering safety.
Okay, so we understand the seeing through part now. What kind of flaws does RT actually find? What are we looking for?
Good question. RT really shines when it comes to detecting what we call volumetric defects.
Volumetric, meaning they have volume, like three-dimensional flaws.
Exactly. Think of things like slag inclusions trapped inside the weld metal, or gas porosity, basically bubbles caught in the weld.
Little voids.
Right. These things create a noticeable difference in density compared to the solid metal around them, a significant negative absorption difference, as we say.
So they show up clearly as darker spots on the film.
Generally, yes. They're relatively easy to spot because they let more radiation through. Slag can be tricky if its density is similar to the metal, but porosity usually stands out.
Okay, so good for bubbles and chunks of stuff. What about cracks? They sound pretty serious.
And this is where it gets really interesting and frankly critical. Radiography is much, much less effective at finding planar defects.
Planar, like flat flaws.
Yes, things like cracks, or lack of fusion between weld passes or between the weld and the base metal. These are essentially two-dimensional separations.
Why are they harder to see?
Think about the radiation beam passing through. If that crack is oriented, say, parallel to the beam or nearly parallel,
it doesn't change the thickness the beam travels through very much.
Exactly. Imagine trying to see a sheet of paper edge on. It has almost no thickness in that direction. A crack can be like that to the radiation.
Wow. So RT could completely miss a dangerous crack if it's not lined up just right.
It absolutely can. That's probably RT's single biggest limitation in terms of defect detection capability. Orientation is critical for planar flaws.
That seems significant.
It is. However, RT has a major redeeming quality.
Which is?
The permanent record. That piece of film, the radiograph, is a physical, tangible record of the weld's condition at that moment.
Ah, right. You can keep it, archive it, review it later.
Precisely. Great for audits, for comparing changes over time, and even for assessing a specific welder's skill or consistency. That permanence is a big reason why it's often preferred, especially for new construction projects.
Okay, so pulling back to the bigger picture, RT gives you that permanent image. It works on pretty much any material, and it's good at sizing those volumetric 3D flaws.
Correct. Those are the key strengths.
But the downsides are pretty serious, too.
They are. You've got the health hazards from radiation. That means classified workers, medical checks, strict safety zones.
And the sensitivity to defect orientation, meaning it can miss those critical planar flaws like cracks.
Right. Poor detection of planar flaws or very fine cracks. Plus, you nearly always need access to both sides of the object.
One for the source, one for the film or detector.
Exactly. That can be a real headache in some situations. Interpretation also takes skill. Reading those films isn't always straightforward.
And it's not instant, is it? You have film processing time.
Correct. It can be relatively slow compared to some other methods. And the equipment, especially high-energy X-ray gear, can have high capital and running costs.
You mentioned different techniques for pipes, too. SWSI, DWSI.
Ah, yes. Briefly. Single wall, single image, double wall, single image, double walls, double image. Those just describe different ways to position the source and film relative to the pipe wall, depending on the diameter and accessibility, to get the best view through the weld. Different geometries need different approaches.
Okay, makes sense. So that's radiography, seeing with radiation. Now let's pivot. Let's talk about ultrasonic testing, UT, listening for flaws.
That's a great way to think about it. UT uses sound waves, but very high-frequency ones, typically above 2 megahertz, way beyond human hearing.
And how does sound help find flaws?
It works on a really neat principle. The speed of sound in a specific material is constant, basically, and sound travels in straight lines assuming the material is uniform, homogeneous.
Okay, so what happens when it hits something that's not uniform, like a defect?
Exactly. When those ultrasonic waves hit a boundary, maybe the edge of the material, or crucially, a defect inside, like a crack or inclusion.
A boundary between materials with different acoustic properties.
You got it. When the sound hits that boundary, some of it reflects back, like an echo. Some might refract or scatter. It obeys the same basic laws of physics as light waves hitting a boundary. Reflection, refraction.
So you send sound in and listen for the echoes.
That's the core idea. By analyzing the pattern of those returning echoes when they come back, how strong they are, an experienced operator can figure out a lot.
Like what kind of defect it is.
Yes, they can often classify defects. Is it slag? Is it lack of fusion? Is it a crack? And really powerfully, they can determine its position very accurately.
How accurately?
Three-dimensionally. You can find out how deep the flaw is, where it is along the weld, and its size, because you know the speed of sound, and you measure the time it takes for the echo to return.
Time of flight. That gives you the distance.
Precisely. So you get depth information, which is something RT struggles with on its own.
That sounds incredibly useful. What about the equipment? Is it bulky?
For standard manual UT, it's actually quite portable.
Sure.
You typically have a flaw detector unit, a box with the electronic screen controls, and a handheld probe connected by a cable.
And the probe makes the sound.
It receives it, yes. It uses a piezoelectric crystal. Amazing little things. Apply electricity, they vibrate mechanically to make sound. Sound hits them, they vibrate and generate electricity.
Converts energy back and forth.
Exactly. Now, there have been huge strides in automated UT systems, too.
Ah, okay. Less manual.
Right. These are often bulkier, using multiple probes, maybe arrays of crystals mounted on manipulators or scanners. They generate a ton of data.
More complex, but faster, maybe.
Potentially much faster and more repeatable, especially for large areas or many identical inspections. Think pipelines again. Historically, the data volume was massive and setup complex, but
Things have improved.
significantly. Newer automated systems are much smarter about data handling, easier to set up. It's making automated UT a really serious competitor or complement to RT in many high-volume applications.
So let's talk detection. What does UT excel at finding?
Well, UT is great because it can find both surface defects and, importantly, subsurface defects deep inside the material.
Oh.
And crucially, remember how RT struggled with planar defects like cracks?
Yeah, the orientation problem.
UT is generally very good at finding those planar defects. Cracks, lack of fusion. These are often strong reflectors for ultrasound, even if they're thin. That's a major advantage.
So it finds the things RT might miss.
Often, yes. Plus, you get that direct location and depth information, the 3D positioning. Results are typically instant, right there on the screen.
And you don't always need access to both sides.
That's another big plus. Often UT can be done entirely from one side of the component. Huge benefit in many practical situations.
And safety-wise, no radiation hazards.
Correct. It's generally considered very safe. You can usually have other people working nearby without needing exclusion zones or special precautions like with RT.
Okay, UT sounds pretty amazing then. Finds cracks, gives depth, one-sided access, safe. Why isn't it used for absolutely everything? What are the catches?
Excellent question. Because there definitely are limitations. Probably the biggest one is the reliance on operator skill.
More so than reading an X-ray film?
Generally, yes. Interpreting those complex echo patterns on the screen in real time, distinguishing between different types of flaws, understanding background noise. It requires a very high level of training, experience, and judgment. The operator is critical.
Okay, skill dependent. What else?
Surface condition is important. The surface where you put the probe needs to be reasonably clean and smooth to get the sound into the material effectively. Rough or scaly surfaces are a problem.
Need good contact.
Exactly. And careful calibration of the equipment is essential for accurate results. You need to set it up correctly for the specific material and geometry you're testing.
What about the record keeping? RT had the film.
Right. Standard manual UT typically doesn't produce a permanent physical record like a radiograph. You get the interpretation on the screen, and the operator writes a report.
But automated systems might be different.
Yes, advanced automated and semi-automated systems often digitally record the raw ultrasonic data, creating a comprehensive electronic record, so that gap is closing.
Any other limitations? Types of flaws it misses?
It's not great for characterizing porosity. Lots of small scattered bubbles don't give clear, distinct echoes like a crack does. RT is better for seeing the overall extent of porosity.
Okay.
And it struggles with very thin materials, say less than about 8 millimeters thick. There's something called the dead zone right under the probe.
Dead zone.
Yeah, it's a small region near the surface where the initial sound pulse and reflections from the surface itself interfere, making it impossible to detect flaws very close to where the probe is placed.
So you can't inspect right up to the surface easily?
Not easily with standard techniques, no. Also, UT is primarily used for ferritic materials, steels, mainly. It's generally not ideal for materials with very coarse grain structures, like some castings or certain alloys, because the large grains scatter the sound waves too much.
Ah, okay. So material type matters too.
Definitely. RT is more universal in that regard.
This really brings us to the core idea then, doesn't it? It's not RT versus UT, it's RT and UT, choosing the right tool.
That's absolutely the right way to think about it. They aren't really competing head-to-head across the board. They complement each other beautifully.
Where one is weak, the other is often strong.
Exactly. RT struggles with those planar defects, the cracks and lack of fusion, especially if they're oriented poorly. UT excels there.
But RT is better for the volumetric stuff, like porosity.
Generally, yes. RT gives you a good overall picture of porosity distribution, while UT might struggle to characterize it well.
Portability-wise.
Gamma RT and manual UT are both pretty portable. X-ray units, especially powerful ones, tend to be less so.
Safety is a big one. UT is safe for nearby workers.
Right. Well, RT always involves radiation hazards and the associated precautions. Big operational difference.
And the record. RT gives you the film, the permanent physical record.
Historically, a huge advantage for RT. UT traditionally relied on the operator's report, though, as we said, digital records from automated UT are changing that game.
So, practically speaking, what drives the choice?
It's often a mix of factors. Technical capability. What kind of flaws are you most concerned about finding? Planar or volumetric?
Cost comes into it, presumably.
Absolutely. RT often has higher capital costs for equipment and potentially higher running costs due to safety requirements and consumables like film or isotope replacement. UT can be cheaper in many scenarios.
Access is another one we mentioned.
Crucial. Does the job allow access to both sides? If not, UT might be the only viable option or requires specific RT techniques like DWSI.
And operator skill.
A big differentiator. RT interpretation, once the film is produced properly, is arguably less operator-dependent than real-time UT interpretation, which demands extremely high skill.
And finally, the material itself.
Right. RT works on almost anything. UT is best for ferritic materials, less effective on coarse-grained stuff.
So it's a complex decision matrix, really.
It is. Engineers have to weigh all these factors: defect type, access, cost, safety, material, required sensitivity, need for a permanent record to choose the optimal NDT method, or often a combination of methods.
What a deep dive. I think hopefully for you listening, you've got a much clearer picture now of how these two incredible technologies, RT and UT, work.
How they help ensure things are safe, how they check integrity without breaking anything open.
It really is a powerful reminder, isn't it? Sometimes the best way to understand something is to look, or maybe listen, right beneath the surface.
It really is.
Yeah.
And maybe that leaves us with a question to ponder for you. When you think about these strengths and weaknesses we've discussed,
Yeah.
RT's struggle with cracks, but great record. UT's strength with cracks, but reliance on skill. How do you think that practical reality influences decisions? Not just technically, but in terms of project risk, cost, and safety management on real-world engineering jobs.
That balance between finding everything possible versus what's practical, affordable, and safe to implement.
Exactly. Where do you draw the line? What level of assurance is good enough? It's not always an easy answer.
Definitely something to think about. That's all for this deep dive. Until next time, keep that curiosity well informed.